Failures follow the same rule as water. They spread wherever there is a path. So, the key to designing fault isolated systems is to break the system down into separate isolated compartments. This means if there is a failure in one area, it will not spread to other areas and take everything down. But there is a practical challenge. Software systems cannot always work in complete isolation. Services need to communicate with each other and they often need to use shared resources. And this means we are opening paths for failures to spread again. So, we use a gate to disconnect. We disconnect when failures start to spread and reconnects when the system is healthy again. So, the idea behind fault isolated system design using the water rule is simple. Where possible, keep services disconnected by default. And where they must be connected, make sure that they can be temporarily disconnected when failures start to spread. Now I will show you how we can actually design real software systems with fault isolation. We will start with a monolith and in the next 10 minutes, we will turn it step by step into a fully fault isolated system design. By the end, you will have a set of patterns and tactics you can use to design fault isolated systems in almost any scenario. So this is the monolith. It contains all the feature in one place and it is deployed on a virtual machine. Now, one feature starts getting heavy traffic. It consumes more CPU, memory or network. And eventually that feature may stop working. But other features will also start failing too. Because if the CPU is high, it's high for everything running on the same machine. So to fix this, we can decompose the system into separate runtime components. Now, if one feature consumes too many resources, only that feature is affected. The rest of the system can keep running. Note that you can use any decomposition technique based on your fault isolation needs and other quality attributes. For example, you can use microservices architecture and decompose the system by business capabilities. Or you can use cell-based architecture and divide the system by customer, region, tenant, or any other partition key. Or you can use a different strategy. But what's important to understand is this. Fault isolation is a runtime quality. So, for example, if you decompose the system into 10 microservices, but deploy all of them together on the same machine, you will not get fault isolation because everything is still running in one place. So failures can still spread. But if you keep them separate at runtime, the failures can be contained. So that is the first step in designing fault isolated systems. Decompose the system and run each part on separate isolated resources. And that is the master key. Resource isolation. But even if we keep components isolated, there is still a problem. These components need to communicate with each other. And this creates new paths for failures to spread again. Let me show you how this actually happens in software systems. Say one service calls another service using an API call, and that downstream service is unavailable because of a deployment or some bug or any other reason. What will happen? The service that depends on that service will also fail, and failure starts to spread again. So what is the fix? We can use the circuit breaker pattern. When the downstream service starts failing, we open the circuit. Technically, this means we stop calling the actual service and we live without it for a while. Maybe we return a default value, or we use cached data, or maybe we use a fallback mechanism. But the idea is simple. As long as the downstream service has a problem, we protect the caller by disconnecting from it. And similarly, the problem can also travel in the other direction. Say the caller service is running under high load, and because it depends on another service, it keeps calling the downstream service. This pushes a large amount of traffic to the downstream service, more than it can handle. In that case, the downstream service can use backpressure. This means it tells the caller, I cannot handle more requests right now. One way to implement this is rate limiting. For example, the downstream service may accept only 1000 requests per minute, and any request above that limit is rejected immediately. This prevents the failure from spreading in the other direction. And this is how two components can communicate with each other while still preventing failures from spreading. This is how you preserve fault isolation during synchronous communication. But a better approach is asynchronous communication. In asynchronous communication, you use a broker as a middleman. So rather than interacting directly, one service puts its messages into a queue and the other service picks them up from the queue. Now, if the downstream service is slow or down, the caller does not have to wait for it. It can keep placing messages in the queue. As soon as the downstream service becomes available again, it starts picking up the messages at its own pace. That's why failures are less likely to spread with asynchronous communication. And this is why asynchronous communication is highly recommended in fault isolated systems. I already have a full video on asynchronous communication or messaging. Next, we have one more challenge. Although asynchronous communication makes failures less likely to spread from one service to another, the broker itself can become a single point of failure. So, what if the broker itself goes down? Everything that depends on the broker will be impacted. So, to handle this, we need to design the broker to be highly available and scalable. And of course, it is much easier to make just one service highly available, scalable, and fault tolerant than to do the same for every service in the system. Many systems use managed cloud services to address this challenge. In addition, we can also use a fallback mechanism, which means we can use messaging or asynchronous communication as a first choice. But if the messaging system itself is down, we can fall back to direct API calls with circuit breakers and backpressure in place as discussed. This gives the system another path to continue operating. Through fallback, we reduce the risk of having a single point of failure. Next, when we talk about resource isolation, it's not only compute resources that we need to isolate. What about databases and other shared resources? Services that share the same database create a path for failures to spread. For example, one service may run data-intensive jobs. This slows down the database. And another service using the same database starts getting slow responses. And now that service has become slow too. See how failures keep following the water rule. So the key is to close the path, either permanently or when the failures start to spread. In the case of databases, it is usually better to use separate dedicated databases from a fault isolation perspective, just like we have done here. This leads to a more fault isolated system design. But of course, not all resources can be separated. Some resources may need to be shared for other reasons, maybe a cache, maybe file storage. In such cases, we close the path when there is a failure. So in the case of a cache, we first try to read the value from the cache. But if the cache itself is broken, we get the data directly from the database. The similar idea applies to storage. If the storage service is broken, we can return a default value or use a fallback mechanism or allow a partial failure. Which means instead of failing the full request, only the part that depends on the storage will fail. The rest of the request can still work. This allows the system to keep working in a degraded mode instead of failing completely. Now, the final concern is how to serve this fault isolated system to clients. From a fault isolation perspective, it is ideal if clients can talk to each component directly. If we can do this, it gives us a stronger fault isolation. But in many systems, this creates other challenges on the front end. And as software architecture is mainly about finding the right balance among different quality attributes, in cases where direct communication is not practical, we can use a router or gateway to pass requests to these components. But with that, we face the same problem again. Failures have found a path to spread again. Suppose one component starts receiving heavy traffic, and since all requests are coming through the router starts getting overloaded too. And now, if the router is impacted, every component behind is also impacted. Because if everything is being served through the same router, and if the router itself fails, the whole system can become unreachable. What is the solution? One thing we can do is keep the router minimal. The router should only route the request, nothing else. The heavy work should happen inside the component, not inside the router. So even if one component is under heavy load, the router is doing much less work. This means the router can stay healthy for longer. This does not fully isolate the failure, but it delays the failure. It simply gives the router more time and capacity before it gets affected. In addition, we can also scale out. This means adding more router instances to increase capacity. This further delays the failure and makes the router less likely to get overloaded. In addition, we can also use fallback mechanisms or allow clients to communicate directly with components when needed. We can also use a hybrid approach. For example, for some clients with higher fault isolation requirements and enough tolerance for complexity, we can use direct communication. And for simpler clients that cannot handle that complexity, we can use the router path while keeping the router minimal and highly scalable. That's how we design fault isolated systems using what I call the water rule. The master key for designing fault isolated systems is resource isolation. Wherever you can achieve full resource isolation, you get fault isolation almost by default. But when full isolation is not possible because components need to communicate or share resources, then you need other patterns and tactics to stop failures from spreading. In this video, I have tried to give you a full decision framework for designing fault isolated systems in different scenarios. And as I said, resource isolation is still the master key for designing fault isolated systems. And there is one architecture that strongly leverages the idea of resource isolation and is especially known for fault isolation: cell-based architecture. It divides the system into multiple runtime cells in a way that each cell can operate almost independently, which means the components don't need to communicate with each other. And as a result, it reduces some of the extra complexity that comes from communication between the components. Let me know if you think I should make a separate video on cell-based architecture.